Hi everyone, welcome back. So today we're going to be talking about Laplace transforms for periodic functions. This turns out to be pretty useful because often when we do apply Laplace transforms at systems that have a natural period, such as spring systems that we've studied before, also electrical systems that are modeled by the same equations. And the forcing functions that we apply to those things are often also periodic. Wave functions or periodic forces being applied to a spring or things like that. Things that have a natural frequency of their own. So it's useful to be able to deal with these things in the Laplace realm. And it turns out that with periodic functions, we have a little bit of extra functionality because periodic functions repeat themselves. So in some sense, understanding what happens on one period should tell you everything you need to know about that function. And it turns out that we can indeed come up with a formula for calculating Laplace transforms of periodic functions by only looking at a single period. And that's the formula we're going to be dealing with now. So let's begin by supposing that we have a function f of t that's piecewise continuous, and it's a periodic function with period t. So we don't have to worry about things being exponentially bounded here, because if it's going to be bounded on the period because it's piecewise continuous, and by definition the limit has to exist at all points. And then that will continue and repeat itself. So it's easy to come up with an exponential bound. In fact, you can come up with a constant bound. It's just a bounded function. All right, so we have this formula that the Laplace transform of f of t is going to be equal to the integral from 0 to capital T of f of t minus times e to the minus st dt divided by 1 minus e to the minus s capital T. So let's go ahead and prove that this is in fact the correct formula by just calculating. So we start with the definition. We want to take the Laplace transform of f of t of s, and that will be equal to the integral from 0 to infinity of f of t e to the minus st dt. And now we're going to break this up according to its period. So we're going to break it up into sections, 0 to t, t to t plus t to 2t, 2t to 3t, and so on, sections 1 period long each. So this is equal to the integral from 0 to t of f of t e to the minus st dt plus the integral from t to 2t of f of t e to the minus st dt. And that will keep going forever, basically. And so we could rewrite this as a summation. It is the sum from n equals 0 to infinity of the integral from n capital T to n plus 1 capital T f of t e to the minus st dt. All right, so we're going to have to deal with this integral here. And so we're going to calculate that thing separately and then bring it back to this summation. So a reminder of the formula that we're eventually going for is there. So let's look at the integral from not from 0, but from nt to n plus 1t of f of t e to the minus st dt. So we're going to try to make a change of variables here. We're going to let u equal t minus n capital T. So du is equal to dt. All right, the idea here is to take from the period that's later on and shift it all the way back to the first period from 0 to t. So the integral becomes, well, if t is equal to nt, then u is equal to 0. So it's the integral from 0 and to t of f of t, not t. Right, so because u is equal to t minus nt, t is equal to u plus n capital T. So this is the function f u plus n capital T times e to the minus s times u plus n capital T du. All right, so what can we do with that? Well, we have a couple of things that we can do. So first of all, f of u plus nt is the same as f of u. Because the function is periodic, it just repeats itself, so it doesn't matter which period we're on. So we go from 0 to t, f of u, and then we have e to the minus su, e to the minus s n t du, right, just by breaking up that exponential. All right, so carrying on here, this will be equal to, we can bring out the things that don't have u's in them, e to the minus s n t, integral from 0 to t, f of u, e to the minus su du, and that is equal to e to the minus s n t, integral from 0 to t of f of t, e to the minus st dt, right? Because it's a dummy variable, we can switch it back to t for convenience sake. Okay, so going back to our formula for the Laplace transform, we have that L of f of t is equal to the sum from n equals 0 to infinity of e to the minus s n t, integral from 0 to capital T, f of t, e to the minus s t dt. Now this part has no n's in it, so it can be brought out of the summation, just factoring it out of every term. So this in turn becomes the integral from 0 to t of f of t e to the minus st dt times the sum of e to the minus s and t. All right, so we're going to have to continue a little bit. Right, so let's remember what we had here. Let's maybe copy this over. All right, let's bring this along. All right, so that's where we were. That L of f of t is equal to this guy. And so we need to figure out what is the sum from n equals 0 to infinity of e to the minus s n t. Well, we can rewrite that slightly as n equals 0 to infinity e to the minus st raised to the n. So you may recall that we have a geometric series formula. This is a geometric series. The r, the ratio is e to the minus st. And so our geometric series formula says that the sum from n equals 0 to infinity of of r to the n is equal to 1 over 1 minus r if the absolute value of r is less than 1. And our r here, this exponential, is less than 1 because it's a negative power. S is greater than 0, t is greater than 0, so e to the negative power. So this becomes equal to 1 over e to the minus 1 over 1 minus e to the minus st. So if we plug that back in up here, we get exactly the formula that we are looking for. The Laplace transform of f of t of s for a periodic function is equal to the integral from 0 to t of f of t e to the minus st dt over 1 minus e to the minus s capital T. So that is our formula, and we can use that to calculate Laplace transforms for any periodic function we like. So we're going to give that a try now. Go with an example. Suppose that we want to find the Laplace transform of this function. So this is from the textbook. It's given as a graph there, but I've written down the definition. This is a function that has period 4, and it's equal to 3 on the interval from 0 to 2, and it's equal to negative 3 on the interval from 2 to 4, and then it repeats because of the period 4. So the graph of this function would look like this. If I can graph nicely, let's try that again. So it would be equal to 3, and then jump down to negative 3, and then jump back up to 3, and then to negative 3, and so on. And so this is f of t. All right, so can we find the Laplace transform of this guy? And of course, we can. That's the whole fun of it. So what is the formula for f of s? Well, what we've just seen is that it will be equal to the integral from 0 to 4, the period 4, of f of t e to the minus st dt over 1 minus e to the minus 4 s. All right, so let's see what we can do there. Well, first of all, f is defined differently on 0 to 2 and 2 to 4, so we're going to break that into a couple of different integrals. From 0 to 2 times, it'll be 3 e to the minus st dt plus the integral from 2 to 4 of minus 3 e to the minus st dt, and then all of that will be divided by 1 minus e to the minus 4s. All right, so what can we do from there? Well, we can take our antiderivative, so we're going to get minus 3 over s e to the minus st from 0 to 2, plus, and here we'll get 3 over s e to the minus st from 2 to 4. And that's over 1 minus e to the minus 4s. All right, so plugging in, let's see what we get. We get minus 3 over s e to the minus 2s plus 3 over s plus 3 over s e to the minus 4s plus 3 over s e to the minus 2s. Didn't quite fit it in there, but hopefully you know what I meant. Over 1 minus e to the minus 4s. And that's it. That's our Laplace transform for this function. Now, I did want to point out, I did want to kind of calculate with this one a little bit more because there's something interesting that we can show here. So let's see if I copy this. And we head over to another copy of this page. All right, so this is what we got for our Laplace function, but this can actually be simplified quite a lot. And this is a bit of extra algebra that I wouldn't expect you to do normally, but I just wanted to show you where it leads. So what we see is that first of all, we can factor out a 3 over s from everything on the top, and what we're left with is, well, we have two copies of, I got a minus sign wrong there. I gotta go back and correct that. That should be a minus sign right there. Okay. So what we have is we have, first of all, we have 3s. That would leave us with 1. We have two copies of e to the minus 2s. So we have minus 2 e to the minus 2s. And then we have an e plus e to the minus 4s. And on the bottom, we have 1 minus e to the minus 4s. And that's something that we can factor both the top and the bottom here. And what we get is 3 over s times 1 minus e to the minus 2s squared on the top. And on the bottom, we get 1 minus e to the minus 2s times 1 plus e to the minus 2s. Okay, so some things cancel. This guy cancels with that. We have 3 over s times 1 minus e to the minus 2s over 1 plus e to the minus 2s. And this can be actually further simplified or written in a different way. 3 over s times, if I multiply through top and bottom by e to the s and divide top and bottom by 2, I get e to the s minus e to the minus s over 2 over e to the s plus e to the minus s over 2. And these are our new friends. The top is the hyperbolic sine function of s, and the bottom is the hyperbolic cosine function of s. What happens when you divide the hyperbolic sine by the hyperbolic cosine? Of course, you get the hyperbolic tangent function. This is what's called tanh of s. So what we've seen here is that if we take a function like the one that we started with here, which is called a square wave, then what we end up with is a constant over s. So the constant is related to the amplitude, 1 over s times the hyperbolic tangent of s. That square wave thing turns out to be very useful in electronics. And this is the Laplace transform of square waves. All right, like I said, all that extra algebra is just for fun, just for my satisfaction, but hopefully you see that there's a little bit more going on in these equations. It's not just random stuff happening. Okay, so finally, we're going to try and do something a little bit ambitious here and do an inverse Laplace transform for this guy, 1 over s squared plus 1 times 1 minus e to the minus pi s. So when we see this term like this, the divided by 1 minus e to a negative exponential, we should immediately suspect that something periodic is going on. And then this 1 over s squared plus 1 should let us know that there's a sine function involved, right? Because 1 over s squared plus 1 is the Laplace transform of sine of t. So what we're going to do in order to work with this is we're going to start by thinking about this function 1 over 1 minus e to the minus pi s in light of our geometric series formula. Remember, sum of r to the n equals 1 over 1 minus r. So this is that. So we can kind of break this up and rewrite it as a geometric series. It will be the sum from n equals 0 to infinity of, well, our r here is e to the minus pi s, and then that will be raised to the n. Okay, so putting that together with the thing that we started with, the inverse Laplace transform of f of s is equal to the inverse Laplace transform of 1 over s squared plus 1 times the sum from n equals 0 to infinity of e to the minus n s pi, or n pi s. Okay, so how does that help us? Well, it's a summation, and that's a linear operation, so we can pull that out. So n equals 0 to infinity, and then we have the inverse Laplace transform of 1 over s squared plus 1 times e to the minus n pi s. Now, what is this? If we look back at our table of Laplace pairs, then what we'll see is that if we have a Laplace transform of something that's known, like this guy, multiplied by an exponential, then that indicates that we're going to get a shifted version of the original thing. So what do we have here? The Laplace transform, the inverse Laplace transform of 1 over s squared plus 1 is equal to sine of t. And then this indicates shift by n pi units and multiply by h of t minus n pi. So if we put that all together, then what we get here is the sum from n equals 0 to infinity of h of t minus n pi times sine of t minus n pi. That's our function. Whatever that thing ends up being, that is the function whose Laplace transform is the one that we started with. Here. Now, again, I want to go just a little bit further with this and show you what this function actually is, if I can ever copy it correctly. There we go. So let's try this one more time. All right, so there's our f of s. So this is composed of several different parts. So basically we have these things that look like, it looks like you're taking the sine function and shifting it over n pi units, and then it's going to be 0 up to then, and then it starts, right? That's what the step function does, 0 up until n pi, and then it's 1 times this thing after that. So let's just take a quick look. If we had h, let's try a different color here. So if we have h of t sine t, which is when n equals 0, then what is the graph of that going to look like? Well, it's going to look something like this. So let's say that's pi, 2 pi, 3 pi, 4 pi, etc. It starts at 0, goes up, comes to 0, down to 0, up to 0, down to 0, up to 0, etc. So the graph will look like this. And so on. Now the second function that we have would be h of t minus pi sine of t minus pi. What does that look like? Well, it looks pretty similar. Let me see if I can line up my axes here. Might have to write on top of something. All right, there we go. Here's pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. So what this is going to do is going to have the same graph, but it will have been shifted over. It'll start at 0, it'll go 0, and then it'll go up, down, down, up, up, down, down, up. So the graph of this one will look like this, and we go 0, and then we'll continue like that. Now what happens when you add these two things together? Well, the first interval you get the top half of the sine function here, plus 0, so you just see this thing. Right? Then after that you get an above and a below that are exactly symmetric to each other, so they cancel. And this cancels, cancels, cancels. Everything cancels from there out. So the first interval will be, goes up in a hump, the half of the sine curve, and then it'll be 0 after that. But then you keep adding on more things that are shifted over further and further. Right, so the next one, h of t minus 2 pi sine of t minus 2 pi will look similar. So it'll go 1, 1, so it'll start here, up, down, down, up, down, so on. So its graph is like this. Right, so added to the things that came before, it'll go the same, and then it'll start being sine, and then the next one will come and cancel out all except the first bit. So in the end, this function, and so just think about it a little bit. It's a weird little function. So pi, 2 pi, 3 pi, 4 pi, etc. So if this is 1, what the graph will end up looking like is the following. It'll go up and then come down in the normal way, and then it'll be 0. And then it'll go up and come down in the normal way, and then it'll be 0. Up, down, 0, etc. And this is what's called the rectified, the half rectified wave of sine t. Half wave rectified sine t. So strange little function. That's what its Laplace transform looks like. It's more like, again, this is more detail than you needed. I just wanted to show you some of the kind of interesting things that happen behind the scenes with these Laplace transforms. The main thing is we have this trick about breaking up the exponential part so that you can get all of the different periodic things that have to be added together to make the final function, and applying the formula that we started with, right? This big formula for periodic functions, where we have the integral over one period on the top, and then we have a division in